All right, here I'm going to cover the calculations for your titration lab and then approximating the Ka. So a short one here, just to remind you that this is the system that you use in the first semester. This time you're doing HCl plus NaOH. So your balanced equation will look a little different. And what you should do is you should um, um, do the opposite of what we did last semester. So last semester, what do? We first standardized the NaOH using the H2SO4 acid solution. All right. But in all the cases, what you do is you have a concentration and volume of one species that will allow you to find the moles or millimoles of it, and then using that information, go to the other one. All right. So last semester, then let's say you had the concentration of the acid was 0.4 and you pipetted in 25 mils, then you can find that molarity times that volume gives you the millimoles for it, all right? And that milli is just commuting through on this molarity. Now, using dimensional analysis or stoichiometry, we can relate these over. And again, the balanced equation will look different this semester. And now we'll take those millimoles and they're all come from the base that you added. And then for that, you need to kind of follow from your titration. You can graph it or just use it straight from the table using your equivalence point. So you're going to have a different volume here. And now millimoles over the volume in milliliters, we can find the concentration of it. All right. So like I said, this is what you did last semester. And then what you did is after you determined it, you came back and you found your unknown. That's what you're doing this time. All right. So you should know the concentration of the base that you titrated with to get the volume of the base. That gives you the millimoles of your base, go to millimoles of acid. All those millimoles came from the pipette that you pipetted in to the flask, and then get to the concentration. Okay, so another thing they ask for the standard deviation and relative standard deviation. So what you should do is find the concentration of all the acids for each of the trials. So it's really redundant calculation, but it's the better thing to do. So the standard deviation will vary. So you can't, a lot of you're going to realize, well, the only thing that's varying here is that volume of the base. So you can use that. But you'll see you'll get a different number for standard deviation. But one of the cool kind of functions is that it actually spits out the same RSD value. All right. So technically it's okay to use these numbers and see how the RSD is changing, but we want you to go ahead and get that concentration. It just makes it easier if you have an outlier to be able to see how much of an outlier it is and so on for each of the trials. All right. And so now the second question it has is, how do you estimate the pKa of your acid? And for that, that's only the weak acid. What you're going to do is you're going to take, again, knowing that equivalence point that you used for that calculation before for that volume, and you're going to then look at the half equivalence point. And when you do that, you're going to come and look at the pH. And now the pH is going to tell you the pKa. All right. So here's a zoomed in kind of version. So that equivalence point, we come look at the half equivalence point, and we come here and then it's saying the buffer here. So why does that tell us? Well, this is the Henderson-Hasselbalch relationship. And at the equivalence point, you convert all the HA into A minus. And so what about at the half equivalence point? You only convert half of it, right? So half of the HA is gone. And so half of it becomes A minus. So that's why this number falls away. And at the half equivalence point, the pH is telling you what's the pKa of the buffer. Okay, so those are the two main things. Hopefully should be short and easy. Oh, the only calculation you need to do then is convert pKa into Ka. All right, you don't actually calculate the pKa. You just read it off your graph. All right, so that's it.